Okay, in this problem, we are asked a 600 Newton child and a 450 Newton child sit on either end of a 4-meter long seesaw. How far from the 600 Newton child should the fulcrum be placed to ensure rotational equilibrium? So it's similar to the last problem we did with some kids sitting on a plank, but not exactly the same. Okay, let's go ahead and draw a picture. We want this to be in rotational equilibrium. So we want it to be balanced. We want it to be equal, not rotating in either direction. And it says the kids are sitting on the ends. So there's a 600 Newton child sitting on one end. And there is a 450 Newton child sitting on the other end. So what's different here is we're not asked where the child should sit. We're asked where should you put the fulcrum, okay? The balancing point. Where am I going to place that so that it is in rotational equilibrium, so it is balanced? Well, I'm thinking I'm going to have to put it closer to the 600s. I'm going to draw it that way, but we don't know exactly where. So you can kind of draw it wherever you'd like. Then we're going to label some things. The question asks how far from the 600 Newton child. So the distance from here to here. What is that distance? I'm going to label that as X in my picture. Okay. The other piece of information that we have is that the seesaw is 4 meters long. So the distance from here to here is going to be 4 meters. Well, if the distance from one child to the other child is 4 meters, and we're calling this part X, I can write an expression to represent this distance as well. Okay? So think about it. If this is 1 meter, then this has to be 3. Okay? Because you have 4 minus 1 is 3. If this is 2 meters, 4 minus 2, this needs to be 2. If this is 3, 4 minus 3 is 1. So each time I'm subtracting whatever I know this one is. So what I'm doing is I'm taking the total and subtracting whatever I know that one is. So this one is going to be 4 minus X for our distance. So now let's go ahead. We know we want this in rotational equilibrium. We want it to be balanced. One of the things we know about rotational equilibrium is that if an object is in rotational equilibrium, then the net torque is going to be equal to 0. We also know that torque is equal to the force times the distance, lever arm, times the sine of theta. If I look at my picture, there are two forces applying a torque. Okay, I'm going to call the one on the left torque 1 plus torque 2. They need to add up to 0. Okay, well, that means I have force 1 times distance 1 times the sine of theta 1 plus force 2 times distance 2 times the sine of theta 2 equals 0. And there's one thing that I'm missing here, okay? Just like when we used to draw free body diagrams, and then we would look at our picture to determine what direction things were going, if positive or negative, same idea here. This torque, if it was the only torque being applied, would cause a rotation in the counterclockwise direction. So torque 1 is positive, and this torque, if it was the only torque, would cause a rotation in the clockwise direction. So this one is negative. I'm going to carry that down right here just with my force. Okay? So now I'm ready to go ahead and start substituting, except I didn't write down all my givens. Didn't write them out very nicely anyways. So I'm going to go ahead and write those out now. So this is force 1, the weight of the first child, 600 newtons. Distance 1 is X, and theta 1. Again, this is the angle when you start at the point of rotation, go down the object till you get to where the force is being applied, and then go in the direction of the force. Okay, now if this object is in equilibrium, we are going to get a 90-degree angle. So we've got 90 degrees there. Similarly over here, force 2 is 450 newtons. Distance 2, or lever arm 2, is 4 minus X. And the angle is, again, going to be 90 degrees. And now I'm ready to substitute in. So Substitute in 600 times x times the sine of 90 plus, we make it negative because it's going to cause a rotation in the clockwise direction, negative 450 times 4 minus x times the sine of 90 is equal to 0. I'm going to simplify this. The sine of 90 is 1. 1 times 600 is 600. 600 times x is 600x. Then over here, I'm going to simplify as well. This is, the sine of 90 is 1, so I can distribute the 1. Nothing changed. Then I need to distribute the negative 450. So negative 450 times 4 is negative 1,800. And negative 450 times negative x is positive 450x. And that is going to be equal to 0. Now I'm ready to simplify the left-hand side. I have got some like terms over here. 600x plus 450x. So I can combine those like terms to get 1,050x. And then I still have this minus 1,800 equals 0. Add 1,800 both sides, we get 1,050. X is equal to 1,800. Divide both sides by 1,050. And we get x is equal to 1.1 71 hundredths meters, or 1 meter and 71 centimeters. So up here, this is 1.71. So let's see if this makes sense. Okay, we can take 4 minus 1.71 and we get 2.29 meters. Well, intuitively, I would think that the lighter child would have to sit further away to make up for their lack of weight with a longer lever arm. And they do. They have a longer lever arm. Okay, so intuitively it makes sense as well.